Hello and welcome to this presentation of NOREBA. I am Ali from National University of Singapore. Current general-purpose processors hold on to resources longer than necessary. In NOREBA, we propose a better resource management for out-order processors based on true branch dependencies of the program. NOREBA shows higher performance with low overheads in terms of power and area. Out-of-order processors execute instructions out of order, but they use a structure called reorder buffer or ROB that keeps the order of instructions, which is a simple way to provide precise exception handling. Here we assume to have a program with 12 instructions running on a core that the execution time of each instruction is 1 cycle, and long latency loads take 10 cycles to get the data from memory. The size of ROB is 8 entries. Instructions are fetched and inserted to the ROB in program order. The processor always looks at the head of the ROB, and if the instruction at the head has finished execution without any exceptions, then commits and releases the resources of the instruction. You can see if a long latency instruction reaches the head, it will block the commit of all other instructions in the ROB. Full ROB and not releasing critical resources will block the front end from fetching new instruction and as a result hurting the performance. When the long latency load is resolved, then the other instructions can commit one by one and release their resources. This is the in-order commit implementation in almost all current out-order processors. In-order commit is conservative. What if we know that instructions 9, 10, 11, and 12 are independent from the branch in this example? Here's an alternative approach to commit the instructions from ROB. If we know that an instruction is independent from the branch that is waiting for the long latency load, then it can commit and release its resources once its execution is finished and doesn't have to wait for the load and its dependent branch. You can see that we are able to save 4 cycles in this simple example. This approach is called out-order commit. In this work, we answer 3 questions: how to detect branch dependencies non-speculatively, how to implement out-order commit of instructions efficiently, and how to handle exceptions when the instructions are committed out of order. NOREBA proposes a hardware-software co-design to implement an efficient out-order commit processor. We have a compiler path that goes through 4 steps for each branch. First, we find the branch reconvergence point. This is the point in the program that the controller will reach regardless of the branch outcome. Second, we detect control-dependent instructions, and these are the instructions that their execution is dependent on the branch outcome. Third, we detect data-dependent instructions, and these are the instructions that the data will be different if we execute different paths after the branch. At the end, we insert setup instructions to the program to embed the branch dependency information. Set branch ID instruction assigns an ID to the branch, and we use a set dependency instruction to set the branch dependency of an instruction block. In the front end of the NOREBA microarchitecture, we gather the branch dependency of the instructions. When an instruction is decoded, we check if the instruction is a branch, then we update a table called BIT to keep the IDs of branches. And if the instruction is set dependency instruction, then we set a counter called DCT that sets the dependency of the next instruction block. In the backend of the NOREBA, we have a lightweight implementation for out-order commit. The instructions are inserted to the ROB, and when they reach the head, we insert them to an appropriate commit queue based on the branch dependency of the instruction. We have a table called CQT that keeps track of how branches are distributed to commit queues. Then we commit instructions from the head of commit queues. Also, we keep a table of recently out-order committed instructions. This table is necessary because in case of a branch misprediction, we don't want to re-execute the instructions that are already committed. A challenge in out-order commit is exception handling. In this simple if-then-else statement, we predict a path after the branch and commit some instructions out of order after the reconvergence point. However, the problem arises if a branch misprediction happens and we start executing from the correct path and we face an exception. We need to save and restore the out-order committed instructions when the control is given to the OS. We introduce 2 new instructions in order to communicate the out-order committed state of the processor with operating system. NOREBA shows 22% performance improvement over the in-order commit implementations and reaches to 95% of the upper bound of branch speculative out-order commit. NOREBA only shows 4% power overhead and 8% area overhead. Thanks for watching this presentation.